Astronomy Cast, episode 277 for Monday, October 22nd, 2012. Orbit. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Good. So a bunch of people asked me if I had gotten hit by this recent earthquake that happened off the coast of Prince Rupert, and I'm totally fine. Didn't even feel it. No tsunami was generated, so I don't think there was any injuries, no damage. It was a pretty tame 7.7 magnitude earthquake, which is quite surprising.
It's always good when they're in largely unpopulated areas like Canada.
Like Canada, which is largely unpopulated. Now, you had a couple of things that you wanted to mention and kind of shamelessly promote.
Well, I did. So Christmas season is fast approaching, according to my local department stores, which are all terrifyingly filled with Christmas stuff. And we would like to remind all of you that one of the ways that we pay our bills is we sell T-shirts. And if you can please, 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 please go buy T-shirts, this will help us pay all of our server bills. And we're actually running short on funding for our server bills right now.
Oh,
so,
really?
and if you want to donate specifically for server bills, don't donate to Astronomy Cast. Go to Astrosphere, because Astrosphere pays for the servers. So,
right.
Buy T-shirts, donate to astrosphere.org. And we will hopefully keep our servers turned on, and that's always a good goal.
That is the umbrella organization
Yes.
that holds Astronomy Cast and 365 Days of Astronomy and CosmoQuest and all of the fun stuff that we do.
So Astronomy Cast is a joint production of Astrosphere New Media, Southern Illinois University, Edwardsville, and Universe Today. And when you donate to Astronomy Cast, that goes through Southern Illinois University, Edwardsville. That goes to help pay for our show notes. It goes to help pay for Preston to do all of our editing, but that does not pay for the servers. Astrosphere is paying for the servers.
Got it.
So if you want to donate to servers, donate to Astrosphere, and we really need money for that.
Okay. All right. Well, let's get rolling then. So when an object is orbiting the Earth, it's really falling. The trick, as described in the Hitchhiker's Guide to the Galaxy, is how to throw yourself at the ground and miss. There are several different kinds of orbits, and they're good for different reasons, from suborbital jumps to geostationary orbit. Time to learn everything there is to know about going around and around and around. So
I never get to see your intros before we start, and I love that quote from Hitchhiker.
I know. It's a great. I sort of stole it, right? Because it's this quote about flying. That the trick to flying is to just fall at the ground but miss. And the lead character in the books at one point finally figures out how to do this and flies around. But that's really what orbit is, right? Orbit is falling and missing the ground.
It helps to start from a large altitude.
So you know what? I want to go back a bit and we just did a bunch of shows on Newton. I don't think we kind of gave Newton's thoughts on orbit kind of short shrift. So can we kind of have a quick conversation about how Newton figured out what orbit is and sort of piece together what the moon is doing?
Well, so
with cannonballs and right?
It wasn't so much Newton that figured out orbits as Kepler, and then Newton figured out the why of the orbit. So what Kepler had figured out was orbital periods, that orbits are ellipses, and then Newton figured out that there's this crazy force called gravity that causes keys to fall to the ground and causes moons to fall towards the Earth and miss. And the trick is, if you simply drop a set of keys straight down, applying no force on them, just releasing them, they're going to fall straight towards the center of mass of the Earth. The center of mass of the keys is attracted towards the center of mass of the planet. Now, if you instead toss the keys, they're going to move with a certain amount of horizontal velocity, and ignoring air resistance, ignoring friction, things like that, they're going to maintain a constant horizontal velocity while falling towards the center of the Earth vertically. Now, the catch is, if you throw those keys hard enough, they're going to keep going further and further and further, getting further around our curved planet.
You can imagine like shooting those keys out of some kind of gun that shoots keys.
Exactly.
A key gun.
Which in some ways seems more dangerous than cannonballs.
Yeah.
But if you get enough velocity on those keys, they're going to come all the way back around and hit you in the back of the head. And so the catch is they're falling at the same rate that the Earth is curving. And if you get the velocity horizontally just right, they're going to keep falling all the way around the planet and come back to where they started. Now, if
Right.
you
And
keep
so,
adding,
oh, go ahead. So I was actually just going to go into that exact question, right? Which is that if you don't add quite enough force, they're going to spiral inward. But if you
yeah,
add more force than what that perfect balance, then they spiral outward, right?
exactly. So you have, this is the difference between a ballistic trajectory, which is one that hits the planet again somewhere else, orbital velocity, which is one where you end up with anything from a circular to an elliptical orbit, to an escape orbit, which is kind of like Voyager or any other of those interplanetary space probes that got away from the Earth and kept going.
Right, right, and of course these are all all of these are different kinds of orbits that scientists are they have use for different reasons. So we'll talk about some of those. So let's sort of go back to the beginning. And so what was the big leap maybe that Newton made about the moon and
Well,
the
Newton's big
and
leap
gravity,
was the
right?
moon is falling around the planet. Up until then, we knew things orbited. We had no clue why they orbited. We had no clue what held the planets around the sun, no clue what held the moon around the earth. This was all highly mysterious. And it was Newton coming along and saying, whoa, gravity. And putting this idea of forces together, and every action is due to a force. For every action, there's an equal and opposite reaction. Putting all those pieces together, that was what Newton's big breakthrough was.
Right, right. And so you've got the situation where the moon is falling towards the Earth, and at the same time, it's sort of falling around the Earth, and it's this perfect balance. It's always continuously missing, but it's not spiraling inward, and it's not, I guess it's slowly spiraling outward.
It's
But
slowly spiraling
yeah,
outwards.
yeah, but that's sort of a different force that's going on. Okay, great. So let's talk about the kinds of orbits that maybe we'll use, and let's get low to Earth first. And I think something that's actually not in orbit at all is the kind of flight that, for example, Felix Baumgartner just did, right? He didn't orbit
Right,
at all, but he traveled to the edge of space. I am holding up my
exactly.
air quotes, but so what's that?
So basically, there's a certain point where you get high enough above the atmosphere or high enough into the atmosphere, depending on how you want to mince your atmospheric levels,
You can say
where
mince your astronauts, but yeah, go ahead. Yeah.
let's not mince
Oh,
astronauts.
no.
No, mince your atmospheres.
Yep, mince your astrophere. Sure, yeah.
So as you get higher and higher up into the atmosphere, the density of the atmosphere drops. This is something you start to experience just by going to the city of Denver. It gets worse as you do things like climb Mount Everest. As you keep going up, you begin to run out of air. And one of the side effects of running out of air is you run out of stuff to scatter the sunlight and create the pretty blue sky above you. So as you get sufficiently high up at weather balloon altitudes, 50 kilometers and higher, basically, you start to reach the point where you can see where the blue sky ends and the blackness of space begins. And you aren't actually necessarily in space at the point that you can see that transition. That's one of the funky things, is how do you define what space is? And it's not defined by where you go from pretty blue sky above you to stars above you. It's actually defined based on energies, because that's much more mathematical. So when we first start talking about where does space begin, we start with thinking about, well, where do we start to see the starry blackness of space? And that's once you start getting to weather balloon or crazy dude jumping out of capsule altitudes, which is roughly 50 kilometers and higher.
And so, you can see that, I don't know if anyone actually got a chance to watch this live or see what happened, but he tumbled out of the capsule and was totally out of control for the first probably minute or so. And
That
then
was terrifying.
I know, it was really scary. And then you could see he sort of, he was able to sort of get some air wind resistance. He was able to get under control until he was in this sort of nicely controlled flight. And you could really see where he had no atmosphere, and then he had enough atmosphere to start to orient himself and remove that spin. But
Yeah.
yeah, it sounds like it really scared the pants off of them. So okay, so that's your first situation. The next one, right, is that you got like Spaceship One and the upcoming Spaceship Two, which is
Well,
again.
there's actually many more layers to go before you start getting that complicated. So,
What do you
so
mean?
Spaceship One and Spaceship Two, that's just suborbital flight. But then you also have to look at things like, I'm going to mispronounce this because really there has to be at least one mispronounced word per show.
Yeah.
It's the Karman Line. It's at an altitude of 100 kilometers above sea level. And this is another one of those places where we start defining what is space flight. And in this case, it's where we're looking at a lot of energy boundaries, and we're starting to look at so how do you travel? Do you travel using the lift generated by your wings? Do you travel using thrusters and orbital velocities? And it's at this line that the atmosphere gets sufficiently thin that you are now a rocket and not an airplane.
Right, but I think what's really important for people to understand is that with like with Spaceship One, they just go up to this line, the 100-kilometer line, and then come back down, and that is it requires a lot of energy, but it still uses a fraction of the.
Word is there is because there's no orbiting involved. There's simply the going up and the coming back down part. It's
Right, right.
ballistic.
Right, ballistic, and it's using a fraction of the energy. Now, what would sort of scientists? I know scientists like to use. They'll use like sounding rockets and things like that, right? There's some
Yeah.
value to going into a suborbital flight, even like straight up and down, right?
Right. So there's lots of different advantages for when you need just quick data. You can do things to measure radiation levels. You can do things to measure thicknesses of the atmosphere at different altitudes. You can take quick X-ray measurements. So instead of having to launch an orbiting X-ray satellite, you can get basic X-ray. You can also get basic microwave data. By launching yourself up into the atmosphere. Now, instead of using sounding rockets, another cheaper way to go is to actually use the equivalent of weather balloons. Just swap out the sensor package rather, get high enough up and float around. And whereas you have a few minutes with a sounding rocket, you can get many hours out of a weather balloon.
Right, until your balloon pops.
Well, yes, that is a problem.
Yeah. Okay, cool. So that's straight up and down, and I think that's and it's really important, I think, for people to understand this distinction that the energies required to go up and then come back down are a fraction of the energy to actually go into orbit. So let's talk about some more ballistic flight now. I think a great example was like the first American man in space, Alan Shepard. He went on a ballistic trajectory.
Right. And in fact, he and many animals that we'll be talking about in the next show.
Show, yeah, yeah.
So what they did was they basically went up high enough that they could experience zero G, that they wouldn't be up there long enough that they had to worry about food and water because they didn't know if people could eat in space initially. And then just bring them straight back down. And this is what we're looking at for Spaceship Two. This is what we're looking at for a lot of the X-Core commercial stuff. Many of these different tourist flights are all going to be these suborbital flights that go up just long enough that you can see the starry night, that you can experience zero G, that you can make some distance across the ground. Luckily, the planet's also rotating beneath you, but you don't have to get all the way up and all the way around the planet as you do with an orbit.
Right, and then I think you can take that concept even further. I mean, you've got like the horrible intercontinental ballistic missiles, which or futuristic.
You say horrible, and I'm looking forward to the day that we have, I don't know, Spaceship 3 and we can fly to Australia suborbital. I want to be ballistic to Australia.
Of course. Well, and that's the whole point, right? Is like let's remove the nuclear payload and let's replace that with a nice scramjet
and
or
decrease
ramjet.
the velocity of reentry.
Yes. So, I mean, in these situations, like what kind of trajectory will an ICBM take? If you want to destroy Russia, which we don't want to destroy Russia, but let's say the Americans did plan to do that.
Well, so let's say, I don't know, let's not destroy anything.
No.
Let's say that we
Let's send flowers to Russia on a missile.
no, I want to send like news reporters overnight to Australia. This is what I want to do. No,
Sure.
you pick it's not so much an orbit this at this point as throwing a football. So you have three different things that you need to take into consideration, and each of them play a different role. At the most simplistic level, you're trying to pitch it so that it goes up. And then comes back down, and time up is roughly equal to time down. It's that whole football arc. There's usually two different angles that you can pick to get to the same location, so you can go really high and have this nice gentle arc up and over. You can go low, and you have to get much more horizontal velocity to be able to get there before you crash into the ground if you take the lower angle. Both of these are fairly straightforward to calculate. It's one of those things we torture freshman physics students with. The second thing you have to take into consideration as you're calculating these trajectories is our planet is rotating. So the point that you aim at now is not going to be there later. So you have to figure out where the point you're aiming at is going to be as the planet rotates. And in the process of figuring this out, you have to take into consideration that you're... Let me turn off Skype. Sorry, Preston. Audience, turning off Skype. So the third thing that you have to take into consideration is you're moving as well. So as your rocket is getting taken off from the ground is moving, giving you initial velocity. This is part of why we like to launch from places like French New Guinea, from Cape Canaveral, from near equatorial regions, is because those parts of the planet are rotating about the center of mass of the Earth the fastest. If you're aiming from Cape Canaveral or New Mexico, and you're trying to land in South Africa, well, South Africa's going around at a different rate. And you have to take all of these things into consideration in trying to figure out how to get from here to there. And Coriolis forces end up playing a role in all of this because of those differences in rotation rates.
Well, and this really is the the big frontier. I mean, if the people are working on different kinds of this technologies, ramjets, scramjets. If they can come up with something that can go like, Mach 20 or so and be able to handle the atmospheric reentry, then we will be able to do flights from, say, from Los Angeles to Sydney, Australia in just a couple of hours. It'll be
so the thing with this
change.
With the things with the scramjets and stuff is they're still doing those at fairly low altitudes compared to the suborbital flights. So I think the suborbital flights in some ways have a much easier way to go. The only trick is if you want to get from America to Australia, well, that and trying to get from America to Australia, the planet's rotating in the opposite direction that you want it to be for that particular journey. So you can almost imagine a future where it's easier to go from New Mexico to South Africa to Australia. Or that's probably bad, from New Mexico to Morocco to Australia. And
break up the velocity changes a bit.
Well, and you're going in the correct direction around the planet when you do it that way. So as long as everyone's going in the same direction, it becomes a lot energetically easy.
All right, so we're going to kick things up to the next level then and actually go into orbit. So, now we've got a rocket. And I think what's really important here is that it's not about velocity upwards, it's velocity sideways. Right?
Yes. And this is the tricky part, is so you have to get high enough up that low Earth orbit, you're traveling at about 8,000 meters per second. So that's compare that to an airplane that goes maybe 1,500, 2,000 meters a second. For the fastest ones we build. So you're looking at 4 times faster than our fastest airplanes in order to orbit. That's it's harder than you would think to double your speed twice.
Right. And so you're looking at 20,000, 25,000 kilometers an hour to get.
It's about 30,000 kilometers an hour. It's about 20,000 miles per hour.
Yeah. And that's, as you say, almost an order of magnitude more than to try and just go up and come back down. It's a it's a phenomenal amount of energy. And so, really only rockets have the energy output to be able to do this. And in many cases, a rocket is just all fuel. It's having to just burn up all this fuel. Almost all its mass is just fuel to get it into this velocity.
Yeah. And this is one of those things we're trying to figure out. What is the most energy efficient way to launch things is such a difficult challenge without a space elevator. You have people that are trying to use magnetic cannons, where essentially use magnetic fields to accelerate things along rails. You have people who are considering various slingshotting things, although really this is best expressed in Moon is a Harsh Mistress rather than in science reality. You then have all the different rockets.
Yeah.
Yet tethers isn't so much a good way to get off the surface of a planet.
But more
space elevators.
Space elevators boost your orbit.
Yeah. And then there's the matter of do you start from the ground or do you start from an airplane? Mm-hmm. And so there's all different ways to look at doing this. And when you look at our early suborbital testing, it was drop something off the bottom of an aircraft that's 2/3 fuel and pretends to be an airplane and see how high it can go.
Yeah. So then what are the different kinds of orbit? So, what's the low, I guess the first one is the low Earth orbit, right?
Right. So here you're looking at a few hundred miles up, orbiting the Earth every hour and a half or so. And in these low Earth orbits, one of the things that you have to worry about is you're still in a thick enough part of the atmosphere. You're still in the thermosphere up until you get to about 700 kilometers up, that you have to not constantly, but on a regular basis, boost yourself back up because there's sufficient drag from this very, very thin, diffuse part of the atmosphere that it's still pushing on you enough to slow down your orbit and will eventually, like it did with Skylab, pull you out of space. And that's a bad thing when you're trying to stay in space.
Right. So, I know that the space station is constantly having its orbit boosted back up.
And it's constantly also doing things like dodging space debris.
Space debris, yeah.
So they're moving that giant spacecraft way more than you would think about.
So it's really an inherently unstable orbit that any object placed in low Earth orbit really is just on a, it's just a matter of time before it just deorbits itself and crashes somewhere.
Yeah. And so, it's just... It's just bad.
Yeah. So then what's a more stable orbit? Right? Where
Once
do they
you
go
start
next?
getting about 10,000 kilometers up, then you start hitting the point where there's sufficiently little atmospheric leftover bits that you're pretty much good to go up that high. But that's pretty high up. You're still not geosynchronous, but you're starting to get there.
Now, and so what are the advantages of placing a spacecraft into that kind of an orbit?
Well, at a certain level, you need less fuel to stay put.
Right, there's the stability.
But beyond that, at that sort of altitude, it's a kind of weird timing. You're not geosynchronous, so you're just slowly drifting over the planet. You're not synchronous with shadows. It's stable, but it's kind of, I don't know what you're trying to do at that orbit.
Well, I know that in some cases there's like a funny orbit where you can be sort of geostationary several at the same time
that's the
every day.
Melina.
Yeah, right. And so there's a special kind of orbit you can do that it doesn't require as much energy to get to geostationary, but it still gives you a fairly stable orbit. And I know there's also more elliptical orbits. So there's lots of orbits that aren't necessarily perfectly circular. They go in these elliptical orbits where they go way far out. We actually talked about this last week, right, with the XMM satellite.
Right, and the orbit that you were talking about a moment ago, I'm going to say this correctly, dang it, the Melina orbit. It's an orbit that gets used for communications with very northern and very southern latitudes. It comes close to the Earth on one part of its orbit and then goes sufficiently far out on the other side of its orbit that it's moving at roughly the same rate that the planet is rotating. And so this highly elliptical orbit allows it to act like a communication satellite when it's over extreme northern or extreme southern latitudes on the planet, zip around the other side of the planet. And one of the problems we run into with normal geosynchronous satellites is they're happily straight above the equator. And if you want to watch television from Juneau, Alaska, or I don't know, somewhere in Siberia, that's not going to help you because the satellite is so close to the horizon. You're looking through so much atmosphere. So it's with these highly elliptical orbits that you're able to get some sort of a television station or something up over these extreme northern and southern latitudes.
And also, as you mentioned, right, there's the elliptical orbit where the satellite is orbiting, you know, around the equator, but you've also got these polar orbits, right, where the satellite is going pole to pole, and that gives you a chance to sort of get complete coverage of the whole planet.
And one of the neat things that you can do with the polar orbits is you can time them just right so that you're always seeing the planet at the exact same illumination angle. And so that has the benefit, especially if you're a spy satellite, of allowing you to very easily make out differences from orbit to orbit in what you're seeing on the planet below you.
So a lot of spy satellites are launched into polar orbits.
Yes, they are.
Good to know.
There's also a weather satellite, so it's not just,
right.
This is also useful for weather.
Right. And let's go to the sort of the granddaddy of all the orbits, which is the geostationary orbit.
Right. So these are orbits that are always over the exact same point on the planet if they're above the equator. So you can have two different...
Why don't they fall into the Earth then? This is impossible.
Well, so they're orbiting at the same rate that the planet is rotating. It's the same way the moon is going around the Earth at the same rate that it's rotating about its axis.
Right. So the satellite is going around, but you're seeing it, and it appears stationary overhead.
Yes. So these are a little more than 40,000 kilometers up, a little more than 25,000 miles up. And what's interesting is occasionally asteroids, including the week that we're recording this, occasionally asteroids come closer to the Earth than these geosynchronous satellites. And it gives you an idea of how empty space is, that so far we haven't lost any of our satellites to a interloping asteroid. I'm waiting for this to happen. That's going to be such a blast to watch how badly the television news covers it. It needs to be like some dead satellite that gets destroyed by an asteroid, but still, it's one of those things. It's on my bucket list of things to see.
And so, why would you want to put a satellite into a geostationary orbit?
Well, if you put it into a geostationary orbit directly over the equator of the planet, it's going to happily stay over the same point on the planet as the planet rotates. And this means that if you're a communications satellite, you're not budging. Someone points their satellite dish at you, you point your satellite at them, it's a nice friendly uplink. Now, the problem is if you're not directly over the equator, you're going to be oscillating north and south as you go around, but you will stay over the same band of the planet. So you're just going to drift north and south as it orbits. This has its uses as well, but it's not generally what you're going for.
Right. Now, are there any other orbits that are possibly used, especially around Earth? I mean,
well,
we talked about this sort of, an increasing orbit, getting further and further away.
Things get thrown into all sorts of different orbits. It depends on what you're trying to do. There's transfer orbits of all sorts of various kinds. There's it's useful to put things in elliptical orbits that keep them below the radiation belts where they can send back their signals to Earth easier, and then above the radiation belts for doing astronomical observations. This is what X-ray satellites like to do. So there's all sorts of different things you can do depending on what your purpose is. But the big named orbit that we haven't touched on so far is the Hohmann Orbit. It's a type of transfer orbit that requires the least amount of energy in order to get from one type of orbit to another. This is what we use to get from Earth to Mars most of the time.
Yeah, I've seen those animations, right? You got this. You can see like the little spacecraft is a little dot, and it leaves Earth, and it's on this increasing orbit. and then its orbit matches Mars, and then it happens to be in orbit at the same place where Mars is, and so that's how it gets to Mars.
So the goal here is you just create a elliptical orbit where one point on the ellipse is the planet Earth, and the opposite point on the ellipse, because with Earth to Mars, you're increasing your distance from the sun. So closest point to the sun is planet Earth, furthest point from the sun is planet Mars, and the trick here is just timing it so that you end up with Mars and Earth at the points they need to be at the times they need to be at those points. And this is why we talk about launch windows that allow us to get to various planets with the correct low energy transfer orbits.
Right, and that's really the trick, is that you want to use the minimum amount of fuel possible to get from point A to point B. You can always burn more fuel if you want to get there faster, but in many cases there's a limit to how heavy an object. I mean, at that point, the rockets are massive and the payloads are tiny because of the energies involved. So, well, cool. Well, this was great, Pamela. Thank you very much. And I think we've covered orbit top to bottom, back to front.
Sounds good.
So, all right. Well, we'll see you next week.
Okay. Bye-bye.
Bye.
Okay. Was that top to bottom supposed to be a pun?
Top to bottom? No, but it is now. All right. So everybody watching this, we're just gonna save our copies of this, and then we'll take a couple of questions, I think, and then we'll shut this down and do the next episode. So
okay, and there will be getting more coffee involved between the two.
Coffee, right? Export.
It is an absolutely beautiful fall day outside.
Wow. Not getting ravaged by a hurricane.
No, we have crystal clear, beautiful blue skies and orange trees and mushy apples that are half rotten on the tree that the sparrows seem to like to eat.
Okay, so I've saved. Have you saved?
Yep.
Okay, cool. So let's see. A couple of questions. Where do the Lagrangian points fall in? And I guess we didn't really talk about the Lagrangian points on this.
No, but we did an entire episode on those.
Yeah, we did a whole show on the Lagrange.
I hit save and I'm getting whirly rainbow. That's terrifying.
So question here, Trevor Soar Videos asks, is it possible to create a probe that could escape the gravity of our local supercluster and travel to the next supercluster? Or are we forever stuck to our local supercluster because of expansion?
It depends on how long you want to wait. So yes, we could send something. It will take a long time.
Or you invent some kind of exotic fuel and...
Yeah, you just like to make shit up.
Well, no. I'm saying like if you want to do, there's a Hohmann transfer for everything.
But to get to the next... It's still going to take a long time. Even traveling at the speed of light, it's going to take a long time.
Mm-hmm. Yeah, so there is a minimum amount of fuel required to even make the Hohmann transfer possible.
Yes.
And then, if you've got some kind of exotic fuel above that, then you can burn more and more fuel to make that trip shorter and shorter within the laws of physics.
Or you can just use a hydrogen scoop or something like that. Now, it's still going to take a long time, though.
You didn't say it would take a short amount of time. I mean, I guess the question is, are we forever stuck to the supercluster?
No, we're not.
We're not. Right. So the only case we would be stuck is if we were in a black hole. You can escape anything else, assuming you've got enough, fuel handy. Gary Robertson wants to know, why aren't more satellites launched from the equator?
Because there's not enough land that's politically stable.
Yeah. Really, it's politics, right? I mean, the most efficient system is the sea launch system that heads out of Los Angeles takes a barge.
There's more than one. I mean, there's ones that go off of Florida as well.
Yeah, but that's not near. That's still kind of far away from the equator. I mean, the sea launch will go right down to the equator and launches right.
No. I meant there's barges that go off of Florida as well.
Oh, okay. I didn't know that. Yeah. So the
I
sea
think
launch
it's
goes
more
out
a
of
matter
Los
of
Angeles.
submarines that go off of Florida, but yeah.
Right, of course, to launch their flowers to Russia. But right, and so yeah, the sort of most efficient. It is absolutely the most efficient thing you can do is to launch
Yeah,
right from the equator. And unfortunately, when you look at the equator, it's either mostly ocean or it runs through a bunch of politically
politically
unstable
unstable countries.
unstable countries in Africa, South America, and Asia. So it's they do the best they can. But I mean, the one in French New Guinea in South America that's right on the equator, isn't it?
Um, I
Kauru. I think it's
I
called.
don't know. I Google Maps.
Yeah, it's pretty close. I mean, that's why they picked it. So
Yeah.
cool. Okay, well, I think those are the questions that were kind of related to this show. So why don't we shut this down? So just to let everyone know, so I'm gonna shut this broadcast down. And then on the event page, I'm going to remove the embedded graphic for the last show, and I'm going to put in the embedded one for the embedded link for the new show. And so all you have to do is wait about 5 minutes and then reload the page, and you should see the next episode kind of queuing up. And we probably won't take as much time to kind of get prepped and get into it. So we should kind of get through this pretty quickly. So we'll see you again in about 10 minutes, Pamela.
Okay. Sounds good.
All right.